This is the continuation of section 3.5 exercises. Problem 6. Graph the rational function x to the fourth divided by x squared plus 2. We'll proceed as before with problem 5. Let's find the y-intercept. So when x is equal to 0, we have 0 to the fourth divided by 0 squared plus 2. That'll give us 0. And that's the origin. So we got the y-intercept. Let's get the x-intercept. So that's where the function itself is going to be equal to 0. And we'll take x to the fourth divided by x squared plus 2. And we'll set that equal to 0. Again, only the numerator can make a fraction 0. So we'll take the numerator and set it equal to 0. We do get x equals 0, but this is multiplicity 4. And so at the origin, we're going to have the graph touching and bouncing off the origin, not passing through it. What else can we get? Vertical asymptotes. No simplification of the original function is possible, so we'll look at where the denominator, x squared plus 2, is equal to 0. And that would mean then x squared is equal to negative 2, which cannot happen. So there are no vertical asymptotes for this function. Not all rational functions have vertical asymptotes. Okay, what else can we find? We can get horizontal asymptotes. Using the same technique as before, the highest degree term that appears in the denominator is x squared, and we'll divide all terms by that dominant term that appears in the denominator. So dividing all terms by x squared, and then simplifying that result. In the numerator we have x squared, in the denominator we have 1 plus 2 over x squared. Now ask, as x gets very, very large, what does the y-coordinate do? Where does it go? The y-coordinates go to infinity. In other words, the numerator of the fraction continues to get extremely large as x gets big. The bottom will be 1 plus 0, and very large divided by 1 will be very, very large. And this is really describing the end behavior of the function. Also notice, though, as x approaches negative infinity, we get the identical behavior for the y-coordinates, and this is because we have x being squared. And so this is indicating that the graph goes up on the right and it goes up on the left. What we didn't do before, but we will now, we don't have a lot of information. So we'll look for symmetry. And we'll look at y-axis symmetry and compute f of negative x. Upon substituting negative x in the original function, negative x to the fourth divided by negative x squared plus 2, we get back exactly the original function f of x. And that means that we have y-axis symmetry. If we translate this information to the graph below, we don't have a lot. The graph goes up on the right and up on the left. We know that we have a y-intercept at the origin, and it must bounce off the origin. And what's on one side of the y-axis must be the same as on the other side, and that would indicate that it actually looks like a parabola like this. To help verify that, let's plot a few points. F of 1 will give you 1/3, so f of negative 1 would give you the same. F of 2 will give you 8/3, so that's approximately 3. That's the same as f of negative 2. And f of 3 gives us 81 over 11, which is about 7, and that's the same as f of negative 3. So plotting these points on the graph will indicate we have indeed a parabola-type graph but it's a little tighter than what I was originally drawing it. Let's go on to problem number 7. We are asked to find the slant asymptotes for the function. Okay, why does it have a slant asymptote? And this is because the degree of the numerator is exactly 1 larger than degree of the denominator. So we have x squared in the top and x at the first and the bottom. This means we'll need to do some polynomial division and divide this polynomial 2x squared minus 5x plus 7 by x minus 2. So let's see, x multiplied by 2x will give us 2x times x is 2x squared. 2x times negative 2 is negative 4x. We then subtract. That'll give us negative x plus, bring down the 7. And then x multiplied by negative 1 will give us negative 1 times x is negative x. So let's see, negative x plus 7. Negative 1 times x is negative x. And negative 1 times negative 2 is plus 2. And of course we'll subtract. And we'll get a remainder of 5. So that means the original function f of x is given by 2x minus 1 plus 5, the remainder, over x minus 2. And this right here is our slant asymptote. So y equals 2x minus 1 is our slant asymptote. Problem number 8. Companies planning to manufacture wheelchairs, and we have the cost function given to us in dollars by 500,000 plus 400x. Write the average cost function C bar, it is pronounced. To do this, we take the cost and divide it by our variable x, which in this case is the number of wheelchairs. So we take the function as given, 500,000 plus 400x, and divide that by the number of wheelchairs, which is our variable x. And that is our average cost function. We now wish to interpret C bar of 1,000 and C bar of 10,000, the average cost at each of those production levels of wheelchairs. C bar of 1,000 will be 500,000 plus 400 times 1,000, all divided by 1,000. And upon doing the arithmetic, we get 900. So this means our interpretation to produce 1,000 wheelchairs the average cost is 900, and the units are dollars per, or meaning for each, wheelchair. Okay. We're also asked to find C bar of 10,000. So doing the calculation the same as we did above, we get 450. So this will mean that to produce 10,000 wheelchairs, the average cost will be $450 per wheelchair. The last part of problem 8. What is a horizontal asymptote for the graph of C, and what does it mean? Okay, so once again, by dividing all terms by the highest degree term that appears in the denominator, we'll have 500,000 divided by x plus 400x divided by x, and then in the bottom x divided by x. So simplifying that will give us 500,000 divided by x plus 400 over 1. And as x gets very, very large, the average cost will approach the value of 400. What does this mean? It means that the cost per wheelchair approaches, this is the average cost per wheelchair, approaches $400 as more and more wheelchairs are produced. Theoretically, it would take a lot, billions and billions of wheelchairs to produce that average cost, but I think we can get that same result by producing less than 1 million. This concludes section 3.5 exercises.